Dear learners, welcome to the MSBT online learning platform, MSBT Lead Learning at your doorstep. I am Mrs. Sonali Sharigar, lecturer in Electronics and Telecommunication Engineering Department at Agnel Polytechnic, Navi Mumbai. This presentation focuses on Unit 5, Applications of 8051 Microcontroller of the course Microcontroller and Applications with course code 22426. The first unit outcome of Unit 5 is generate the specified waveform using 8051 by given methods. The learning objective of this presentation is to generate square wave on port pin using timers of 8051. At the end of this presentation, you will be able to develop assembly language program to generate time delay using timer, and you will also be able to develop assembly language program to generate square wave using timer. Dear learners, let us learn and understand programming timers of microcontroller 8051, time delay generation using timers, and generation of square wave on port pin using timers. The concept of square wave generation using timers is to toggle the port pin, wait for some time by generating a specific delay using timers, and repeat the process again and again. Learners, in Unit 3 you have learned about timers and counters of 8051, SFRs of timer counters, and you have also developed programs to generate delay using timers and counters of 8051. Here's a quick recap of timers of 8051 for you. You all know that 8051 has two timers, timer 0 and timer 1. Each of the timer is a 16-bit up counter. The timer operates in four modes: mode 0, 13-bit mode; mode 1, 16-bit mode; mode 2, 8-bit auto reload mode; and mode 3, split timer mode. Every timer needs to be loaded with a count, initial count, and whenever the clock is given, the timer count increments at the rate of f oscillator by 12, which is one machine cycle. Means after every one machine cycle, the timer count increments by 1. When the count reaches its final value and rolls over from all ones to all zeros, the timer overflow flag is set. The SFRs which control the timer operation are TMOD and TCON. Here in the figure, you can see TMOD register format. The upper 4 bits of TMOD register control timer 1 operation, and lower 4 bits of TMOD register control timer 0 operation. You must have learned in Unit 3 that gate bit is always kept 0. C oblique T bar bit decides whether you want to use it as counter or timer. So to use the section as a timer, we keep C oblique T bar bit 0. M1 and M0 bit depends upon the mode in which you want to operate the timer. Steps to program timers of 8051 are as follows. Load the TMOD register with a value indicating which timer in which mode is used. For example, if timer 0 in mode 1 is to be used, TMOD should be loaded with hex value 01H. The next step is to load the initial count in TH and TL registers. As shown in the diagram, if the initial count value is FFFCH, then the higher 8 bit of the count FFH should be loaded in TH register, and the lower 8 bits of the count FCH should be loaded in TL register. After loading the initial count, the next step is to start the timer by setting the timer run bit. If timer 0 is used, TR0 bit should be set to 1. As soon as the TR0 bit is set to 1, the timer count starts incrementing by 1 at the rate of f oscillator by 12, which is one machine cycle. Means after every one machine cycles, the count value increments by 1. Next step is to monitor the timer overflow flag to see if it is raised. As can be seen in the diagram, as soon as the timer has started, the count value of timer starts incrementing from its initial value FFFCH to FFFFH. As long as the value of the timer is not become 0, the timer overflow flag is 0. On the next increment, when the count value rolls over from all ones to all zeros, overflow occurs and the timer overflow flag is set to 1. As soon as timer overflow flag is set to 1, monitoring of timer flag is stopped and the TR bit of the timer is cleared to stop the timer counting. Then the overflow flag is cleared in the next step, and at the end we can again reload the value of the count in TL and TH registers to repeat the whole process again. Let us implement the steps to program timers of 8051. Here you can see a program to generate delay using timer 0 in mode 1. The first instruction move tmod, #01h is configuring timer 0 in mode 1. Next, move TL0, #0fch loads the lower 8 bits of the count in TL0 register. Move TH0, #0ffh loads the higher 8 bit of the count ffh in TH0 register. The next step is to start the timer. So the instruction set BTR0 starts timer 0. As soon as the timer is started, the value in TH and TL0 register starts incrementing by 1. So the next step is to monitor the timer overflow flag. Instruction JNB back is used to monitor the timer overflow flag. As long as TF0 flag is not set, the instruction is kept in loop. Whenever the timer overflow occurs, the TF0 flag is set to 1, and on the next step, CLR TR0 bit stops timer 0, CLR TF0 bit clears the timer overflow flag, SJump again reloads the count, and the whole process repeats again. If you note here, the initial count loaded in the timer registers is FFFCH, which in decimal form stands for 65532. Now let us calculate the amount of delay generated by this timer program. The time delay generated by timer is given as 12 by F oscillator, which is time taken for one machine cycle, multiplied by number of increments made by the timer to overflow. Assuming crystal frequency as 11.0592 MHz, time delay is given as 12 upon 11.0592 MHz multiplied by number of increments. Number of increments can be found by the final count minus the initial count. As mode 1 of timer is 16-bit mode, the final count is 2 raised to 16, 65536 minus the initial count loaded is 65532. So number of increments made by the timer to overflow is 4. So time delay is equals to 1 upon 0.85 microseconds into 4, that is equals to 4.34 microseconds. So this program generates a delay of precise 4.34 microseconds. Thus, we can see that timer gives a precise time delay, and the amount of delay generated depends upon the count loaded in timer registers. You have learned square wave can be generated on specific port pin by toggling that port pin. If a square wave is to be generated on port pin P2.0, then the port pin P2.0 should be toggled between logic 0 to logic 1 and again to logic 0 with a delay in between. The delay decides the on time and off time of such a square wave generated. The T on time is the time for which the pin is high, and T off time is the time for which the pin is low. This T on time and T off time delays can be precisely generated using timers. Let us develop an assembly language program to generate square wave of frequency 2 kHz on port pin P2.0 using timer 1 in mode 1. Let us also assume that the crystal frequency is 11.0592 MHz. As the frequency of square wave is 2 kHz, its time period T is 1 upon 2 kHz, which is 0.5 milliseconds or 500 microseconds. A square wave with time period of 0.5 milliseconds will have its T on time and T off time equals to half of its time period, which is 0.25 milliseconds or 250 microseconds. Thus, a delay of 0.25 milliseconds needs to be generated by programming timer 1 in mode 1. Now let us understand the timer count calculations. Time delay generated by the timer is given as 12 upon F oscillator, which is the time for one machine cycle multiplied by the number of increments the timer has to make to overflow. By substituting the value of time delay and oscillator frequency, the number of increments comes around 230. This means that the timer has to make 230 increments to overflow. Now we need to calculate the initial count to be loaded in TH and TL registers. The initial count is equals to 2 raised to 16 minus n. As timer is used in mode 1 and as the mode 1 is 16-bit mode, the final count is 2 raised to 16. Hence, the initial count is given as 2 raised to 16 minus n. By substituting the value of n, we get the initial count as FF1AH. Thus, FF1AH is a 16-bit count which needs to be loaded in TH and TL registers. So, FFH is the higher 8-bit count which is to be loaded in TH1 register, and 1AH is a lower 8-bit count which should be loaded in TL1 register. The two programs for generation of square wave using timers are shown here. Let us understand program 1 first. Move tmod, #10h instruction configures timer 1 in mode 1. Move TL1, #1AH loads the lower 8-bit count in TL1 register. Move TH1, 0FFH loads the higher 8-bit count in TH1 register. As we have calculated in the previous slide, the 16-bit count to generate a delay of 0.25 milliseconds is FF1AH. So we have loaded that initial count FF1AH in the registers TH1 and TL1. Next, the timer needs to be started. So setBit TR1 instruction starts timer 1. After the timer is started, we need to monitor the overflow flag to check whether the overflow flag has set to 1. For doing that, instruction JNB TF1, back is used. As long as overflow has not occurred, TF1 flag is 0 and the instruction keeps on jumping to back and keeps on monitoring the TF1 flag. After 0.25 milliseconds, when overflow occurs, TF1 flag is set to 1 and the program control shifts to the next instruction, which is CLR TR1. This instruction clears TR1 bit, which stops the timer. Then CPL P2.0 instruction complements the port pin. By default, the port pin status is 1. After the time delay program is over, that is after 0.25 milliseconds, by complementing P2.0 bit, the pin status has become 0 now. Then the timer overflow flag is reset. SJump again shifts the program control to again where the timer count is again reloaded and the whole process is repeated. So again after 0.25 milliseconds, when TF1 flag is set to 1, the timer is stopped and complement P2.0 is executed, which makes the pin 1 again. As a result, the pin is kept 0 for 0.25 milliseconds and the pin is kept high for 0.25 milliseconds, giving us a total time period of 0.5 milliseconds and which gives us a frequency of 2 kilohertz. Let us see program 2. Program 2 is same in logic as program 1, but instead of using CPL P2.0 instruction for toggling the port pin, we have used CLR P2.0 and setB P2.0 instructions to make the pin 0 and 1. The first instruction move tmod, #10h configures timer 1 in mode 1. CLR P2.0 pin clears the pin P2.0 and makes it 0. Then a delay subroutine is called. After the delay subroutine gets over, again the pin is set to 1 by using instruction setB P2.0. Again a delay subroutine is called of the same amount and the whole process is repeated. When a delay subroutine is called, the program control transfers to delay, and if you see the delay subroutine, we have written a program for loading the original count FF1AH, starting the timer, checking the overflow flag. Once overflow occurs, we have stopped the timer, cleared the flag and returned back to main program. So the delay subroutine, which is called in between toggling of port pins, is generated using timer 1 of 8051. Let us develop one more program to generate a square wave of frequency 5 kHz on port pin P1.5 using timer 0 in mode 2. And let us also assume that crystal frequency is 11.0592 megahertz. As the frequency of the square wave is 5 kilohertz, its time period t is 1 upon 5 kilohertz, which is equals to zero point 0.2 milliseconds. With zero point 0.2 milliseconds time period, the t on and t of time of such a square wave is 0.1 milliseconds each. Thus, a delay of 0.1 milliseconds needs to be generated by programming timer 0 in mode 2. Let us understand timer count calculations. We know that the time delay generated by the timer is given as 12 upon f oscillator multiplied by the number of increments the timer needs to make to overflow. So putting the value of time delay as 0.1 milliseconds and oscillator frequency as 11.0592 megahertz, we get the number of increments as 92. Means the timer has to make 92 increments to reach its final counts and then overflow. So the initial count to be loaded in the registers, timer registers, needs to be found now. As we are using timer in mode 2, mode 2 is auto reload mode, rather 8-bit auto reload mode. So the final count is 2 raised to 8. So the initial count is given as 256 minus 92. It is equals to 164 in decimal form. It is equals to A4H in hexadecimal form. Thus, the value A4H should be loaded in TH and TL registers. To understand this program, let me first remind you about mode 2 of timer. Mode 2 of timer is 8-bit auto reload mode in which TL register acts as a 8-bit up counter and TH register acts as a register which holds the count. So in this mode, the count is loaded in TH register. When the timer is started, the count from TH register gets loaded in TL register. Then the TL register increments by 1 upon every machine cycle. When the TL register overflows, TF flag is set to 1 and the original count is automatically reloaded from TH register to TL register. Let us now see the program. So the first instruction, move tmod comma hash 02h configures timer 0 in mode 2. Now in the previous slide we have calculated the count to be loaded as A4H. So move th0 comma hash 0A4H loads the 8-bit count in th0 register. Set bit TR0 register starts timer 0. As soon as timer 0 is started, the value from TH0 register gets loaded in TL0 register and the TL register starts incrementing by 1 upon every machine cycle. Then we keep on monitoring TF0, which is timer overflow flag, to check whether overflow has occurred. So JNB TF0 instruction monitors the TF0 flag. As long as TF0 bit is not set, the program is kept in loop checking the status of TF0 bit. As soon as TL1 register overflows, the TF0 flag is set to 1 and the program control is transferred to the next instruction CPL P1.5, which is now complemented. The initial status of P1.5 was 1. Now after complementing it has become 0. So it has taken a time period given by the timer program for complementing, which is 0.1 milliseconds. That means after 0.1 milliseconds, the pin status has become 0 now. Next we clear the flag, TF0 flag, and again we go back to check the flag status. As we are using mode 2 of timer, we never stop the timer. We keep the timer in run mode. When the overflow occurs, the original count gets automatically reloaded. So we don't go to load the count again. Because the count gets automatically reloaded, we jump directly to check the overflow flag. Again, after 0.1 milliseconds when overflow occurs, the pin is complemented. So pin again is made high after 0.1 milliseconds. Thus, the pin P1.5 remains high for 0.1 milliseconds and remains low for 0.1 milliseconds, giving us a total time period of 0.2 milliseconds and frequency of 5 kilohertz. Dear learners, attempt MCQ set 1 and practice worksheet. You can also visit the following YouTube links for further information. Thank you.